I think I should have written a shorter abstract. Okay, so thank you for having me here tonight. It's nice to be back in Edinburgh. So this is where I did my undergrad physics degree many years ago. So tonight I'm going to talk to you about stratiform clouds. So most people, when you say stratiform clouds, they get rather depressed. They think they're the dullest, most boring type of clouds on the planet. And that's probably true, but I get excited by them. Hopefully by the end of this talk, you'll understand why that is. So the reason that we're interested in these clouds is that they're actually electrified. And this is not something that a lot of people know, but by the end of this talk, you will also be experts on this. So the reason that we are interested in these clouds is they become charged, and that charge can influence the cloud microphysical processes inside the clouds, and that may have potential implications for climate. So I'm going to talk you through all that tonight. So we will start off discussing how these clouds become charged, how we know they're charged, and that's through some measurements that we've made with bespoke balloon instrumentation that we've developed at Reading. I'll then discuss what the effect the charge has on the droplet behavior. And then I'll talk about some novel experiments that we've been doing in fogs to demonstrate or to try and find some evidence whether charge affects cloud properties in the real environment. And then finally, I'll discuss what the implications of this are for weather and climate. Because this is very much an understudied effect. It's not included in climate models, and it's not widely studied. So there's lots to learn about it. So we'll start off discussing where the charge comes from, basically. So if you forget everything else I say tonight, the one thing to remember here is that Earth's atmosphere is always electrified. Normally, we just think about charge when there's thunderstorms and lightning around, but it's electrified all the time, and charge is continuously generated. And that's through a process called ionization. So positive and negative charge is created by ionization all the time. And in our atmosphere, there are two sources of ionization. The first is from galactic cosmic rays. So these are highly energetic particles from basically outer space, from outside our solar system, and they enter Earth's atmosphere from above. And as they do so, they create a cascade of charged particles right down to the surface. And because they come from outside our solar system, they're modulated by solar activity. So they respond to magnetic fields. The other source of ionization is radioactivity at the Earth's surface. So this is mostly from gamma radiation from the soil. And so this emits ions which can be transported upwards, but they're typically trapped in the boundary layer. So they're stuck in the lowest kilometer of the atmosphere. So this charge is being generated all the time. And initially, the charge exists in the form of really tiny nanometer-sized charged ions. But they don't stay tiny for long because they interact with atmospheric molecules and aerosol particles and droplets. And this is the subject of a totally different talk, or three totally different talks, but I just wanted to make you aware that charge can actually affect many different types of aerosol and droplet processes. Some of the things that we've studied, for instance, is the charge effect on long-range dust and volcanic ash transport. So the idea here is that the charge can maintain the dust or the ash in the atmosphere for longer than it would be normally. And this might explain some strange observations of large dust particles that are transported huge distances, and nobody can explain why. Another thing that charge might affect is the radiative properties of dust layers. So there's been some theory and measurements that suggest that the particles can align in the electric field and act like a Venetian blind type effect, which affects the amount of solar radiation that's transferred through a dust layer. And then the other thing, which is what we're going to talk about tonight, is the effect of charge on cloud microphysics. So another concept that's important here and that's related to charge in the atmosphere is something called the Earth's global atmospheric electric circuit. So I should probably move this because you can't actually read the title of these slides. So the global circuit, not much better, is it? It's okay, it's fine, good point, it disappeared, sorry. So the global circuit is a hypothetical concept which describes current flow around the planet, basically. Why are we not moving? There we are. Okay, so this was suggested by the Scottish physicist C.T.R. Wilson in the 1920s. So this is the same C.T.R. Wilson who invented the cloud chamber, but he also worked in atmospheric electricity. And in this circuit, we have Earth's surface and the ionosphere, which is a layer in the atmosphere about 60 kilometers up. And these are highly conducting regions. And the idea is that we treat these two surfaces as the plates of a spherical capacitor. And in the middle, we have the atmosphere, which is weakly conducting because of the ionization from the cosmic rays and the radon. And this charge that we have, this positive and negative charge, becomes separated in thunderstorms. So the top of thunderstorms become positively charged and the bottom become negatively charged. And this charge is transferred up into the ionosphere and the negative charge is transferred down to the Earth's surface. This creates a huge voltage difference or potential difference between these two plates of the capacitor, which we call the ionospheric potential. And it's about 200,000 volts. So if you were to connect a wire between the ionosphere and the Earth's surface, there'd be a 200,000 volt difference, which is enormous. And that voltage difference, and because we've got charge carriers, means that we have a tiny little current which flows, which we call the air-earth conduction current, or JC. And it flows everywhere. So it's not just related to thunderstorms. It flows in all fair weather regions of the atmosphere. It's flowing right now. So the two things that you've got to remember as we go through this talk, the two concepts are this vertical conduction current, JC, and also the concept of an electric field. So this global circuit sets up an electric field in Earth's atmosphere, which again is everywhere. And near the surface, it's about 100 volts per meter. So that means there's about 100 volts between my feet and about here. We also call it the potential gradient. So I'll use electric field and potential gradient sort of interchangeably in this talk, but they basically mean the same things. It's just one's the negative of the other. So we've got a conduction current density and we've got an electric field set up by this global circuit. So what evidence is there for this global circuit in the atmosphere? So the idea is it's driven by thunderstorms. So as I say, this idea was first suggested in the 1920s. So in the 1930s and 40s, there was a lot of interest in investigating whether this concept was right or not. But in these days, we didn't have global lightning detection networks. We didn't know where the lightning was over the Earth. What we had was thunder day data. So this is an observer listening, saying, I can hear thunder today, and that's recorded as a thunder day data. So that means there was lightning and thunder on that day. And so through lots of painstaking observations and collating the data from all the observatories around the world, they managed to create this map of global thunderstorm activity. And so you see that there are three main thunderstorm chimneys on the Earth, one in the Americas, one in Africa, and one in Asia. And if you plot the surface of the Earth that's covered by thunder, or therefore lightning, as a function of time across the day, each of these blue curves is these three thunderstorm chimneys. And the time of day that it happens depends on the local afternoon time. So obviously local afternoon is first in Asia because that's when the thunderstorms happen. But when we plot it as GMT, it looks like this. And if you take the sum of all of these areas, then you get this global curve. But we're not used to looking at time backwards, if you like. So let's invert, or let's change it into what seems a bit more sensible to us. So 0 to 24. So the thunderstorm area changes like this throughout the day. There's a minimum in about 3 UT, and there's a maximum about 1900 UT. Now, at the same time, there was a wooden research vessel sailing the oceans called the Carnegie Research Ship. And this was making magnetic measurements and atmospheric electricity measurements. And it was measuring this electric field or potential gradient. And they found that regardless of where they sailed in the world, on a fair weather day, when there was nothing else happening, they measured this diurnal variation in the potential gradient. And it's got a minimum at the same time. Well, you can see for yourself. The two look very, very similar. So not only, so the fact that they measured the same variation globally meant that there was something globally going on. And the fact that this matched with the thunderstorm activity really suggested that, okay, it's thunderstorms that are driving the global circuit. So what does this mean for our clouds? So as I said, this conduction current, which results from the global circuit, it flows everywhere. And when it encounters clouds, it creates, or specifically layer clouds, it creates charge on the edges of these clouds. And I'll describe that in detail in the next slide. But the point here is that this is a very understudied phenomenon. most of atmospheric electricity has studied either thunderstorms or what we call the fair weather region, where there are no clouds. The semi-fair weather region, where the clouds are, has been largely neglected, so we don't know a lot about this. But these clouds cover 30 to 40% of the planet at all times, and there's an awful lot of them over the ocean. So this charging of these clouds is happening all the time, and we don't understand a lot about it.